Hi, my name is Kyle Thompson.
And I'm Flint Yoder,
And I'm Jose Razas.
and we're Group 19, and we're doing the Tetris Clone project. Today we're going to talk about the engineering requirements of our project and then give it an overview of it. Following that, we're going to give some more insight into the hardware of our design and then give a demonstration of it working. And then after that, we'll give some tips for future seniors. In this section, I'm going to talk about the engineering requirements for our project. The first requirements that I'm going to introduce are the display reliability and the project cost requirements. For the display reliability requirement, we had to have at least half of our pixels on our display illuminated for a minimum of 8 hours. To test this, we created a video showing that all of the pixels on this display were able to remain illuminated for over 8 hours. We've uploaded this as proof of our test. The project cost requirement was that the project couldn't cost more than $1,500. We kept a spreadsheet of all of our expenses and proved that we're well within this budget. Two more requirements for our project were that we needed to have multiplayer ability for the games that supported it, which, showing Tetris and Python, we have, and this goes along right in hand with our next requirement that we need to have a good controller definition. So each controller has to have the 4 cardinal directions as well as at least 2 other inputs, A and B. So here we have both 1-player and 2-player controllers can control the block and use its A and B button to rotate, and that's how we proved that our multiplayer is multiplayer capable as well as having a controller definition. Next 2 requirements that we have for our project are the screen resolutions and the screen visibility requirements. For the screen resolutions, we needed a minimum of 10 by 20 pixels to play Tetris because that's its native resolution. You can see on our display here that we have, we're meeting that with 16 by 24. The next is the screen visibility. We needed people with 20/20 vision to be able to easily view the words on the screen from at least 20 feet away. And we found that users are able to do that. The next requirements I'll talk about are the number of games requirement, which we're required to have at least 2 playable games on our device, which you can see we have Tetris and Python here, as well as the next requirement being the external memory. We're required to be able to add more games with the external memory. Here I'll show with the USB device I have in my hand, and I navigate to the external memory device menu and plug it in. The processor picks up that there's a game file on the external memory device, proving that our external memory interface is working. The last 2 requirements I'm going to talk about are ones that we have currently not met. Our screen size requirement requires us to have a 2 feet by 4 feet display. Our current display is only about 1 1/3 feet by 2 feet. The other requirement that we have not yet met is the ease of use requirement. Our requirement was that 9 out of 10 people who use the device could navigate through the menus to the game they wished to play in approximately 30 seconds. Now, when we took the survey of people and had them come use our device, only 7 out of the 10 we chose were able to do this. This is a mixture of some usability issues we've run into that we're working on, as well as the size requirement not being met, making it hard to read the words on the screen.
Now let's take a look at the top-level block diagram for the Tetris Clone machine. Upon viewing our project, 2 different things are noted. We have 2 different cases, the podium case and the display case. The display case is meant to be tucked away behind a panel of frosted glass so that the display appears to be more diffused. This will make our display look better. The podium case is meant to be out in a common area so that users can easily interact with our system. Now, because we have 2 different cases, we need 2 different power supplies, the podium power supply and the display power supply. The difference between the 2 is that the display power supply has more voltage rails so that it can power all of the hardware within the display case. Also, the display power supply needs to be able to source more current to the display because it takes up more power. Now let's take a look at the main flow of operation for our project. To start, the users input data to the controllers by pushing buttons and moving joysticks. This, in turn, generates controller data that is sent to the main control unit. Now, depending on the state that the main control unit is in, it will interpret this controller data and then determine the appropriate data to send to the display driver. The display driver is used as a frame buffer, which means that the main control unit is only sending pixel updates to the display driver, and the display driver is the one responsible for actually driving the display. It constantly sends the data needed for the LED array display so that it has a refresh rate of about 60 Hz. This allows the main control unit to only send a very limited amount of data, which frees up program execution.
In this part of the video, Flint will navigate our menu. Here's our main menu, which contains of games and settings. Flint is going to select the games menu, and in the games menu we have Tetris, Python, and external memory, which is down here, and we will talk about later. Flint is now going to play Tetris. Flint is now going to end the game. Next, Flint will play Python. And Flint just ended Python. Now we will demonstrate our external memory, which works by pulling. Our computer constantly pulls for a USB flash drive. And we will insert our USB flash drive, and as you can see, it will appear here. Flint will now play Tetris that's on our flash drive.
Now Flint's going to play Tetris, and while he's playing, I'm going to explain the gameplay a little bit and how it may differ from traditional Tetris. So, in our Tetris game, we have all of the standard Tetris pieces. So he's already spawned a T block, a Z block, and a square block. There's also the line piece, the S block, the J block, the L block, etc. So as he places blocks, whenever he completes a full row, his score will increase depending on the number of rows he completes at any given time. So if Flint can actually build up a line completion here, we can show the line completion functionality here. So right now he's got 2 rows that he's completed, and notice how they cascade down like normal Tetris would. In that case, since he completed 2 lines at the same time, his score increments by 4. Now the way that we've set up Tetris is that your score increments by the number of lines you complete at any given time squared. So if you complete 1 line, your score increases by 1. If you complete 2 lines, your score increases by 4. 3 lines is 9, and 4 lines is 16. This gives more incentive for users to try and complete 4 rows at the same time, which is called a Tetris. So yeah, that's the general synopsis of Tetris, and now we're going to move on to Python. Now Flint will demonstrate Python. Python is based off a game called Snake, where a user is controlling their red snake, and they run over apples to increase the size of their snake. So as the game continues and their snake grows larger, the game gets more and more difficult because the user has to avoid themselves as they try and collect more and more apples. So in this case, Flint ran into himself, which is why the game ended. The user can also run into a wall, which will also end the game. Now we're going to take a look at the options the user has, which is to add games to the system using our USB memory unit. So Flint has navigated to the external memory menu, and what this is waiting for is when a USB device is plugged into our system, the Raspberry Pi will constantly poll that device for valid game files, and when it finds them, it will appear on our menu. So when a valid game file is on our USB memory device, the user can then select this game and play it directly off of the USB stick. Now you can see this version of Tetris is actually one that's meant for a full-size screen, so the blocks are much larger.
These are our cases, this is our podium, and this is the display. They were built to be lightweight and durable, so they were built out of 2x4s and a really thin sheet of wood. The display case is 8 feet tall by 4 feet wide and is about 2.5 feet in depth. The reason it's 2.5 feet deep is because we needed stability to prevent it from. So these are our controllers, 4 push buttons, a player 1, player 2 button, and 2 joysticks. And inside the podium case is a microcontroller, which is constantly polling for user input. Once it receives user input, it then outputs it through this 50 feet long serial cable into the computer.
Here I'll show a little bit about the making of the different panels to make up the display. First we start with a section of the panels. It's got 0 LEDs in it. Next stage is to put all of the LEDs in, connecting the anodes. Here we see all the LEDs are in, beginning to be wired up here. Next panel, everything has been wired up, connecting all of the different cathodes together, as well as all the anodes. After that's been completed, we move on and attach the different PCBs. There are 6 LED drivers here and here. There's a microcontroller that controls everything, and there's a shift register allowing us to multiplex through 8 different rows at a time, and there will be 3 different boards with transistors on them to allow us to source the current necessary for the different LEDs. So here are a few stats for the different panels of our display. Each panel consists of 16 by 24 LEDs, which makes up 384. Each LED has 4 different leads coming off of it, and along with the 11 PCBs, that makes up a total of around 1,600 connections per panel.
So one of the cool things about this project is that the software written for it is completely portable. So right now I'm about to run this on my Windows computer, which is what I actually originally developed it on. So since this is programmed in Python, any system that's running a Python 2.7 interpreter can run this code, along with a couple other libraries. So as we can see, if we take a quick shot over to the game menu, it's trying to output all of this data on my HDMI display. So right now that looks like it's in the games menu, so if I were to navigate to the games menu on my laptop, here we can see that I've got Tetris, Python, my external memory option, as well as going back to the main menu. So this was kind of how all of the software was developed and how it would work on a laptop. So as we can see, I can go into the games menu again, and I'll still play games like Tetris. But now it's on a display that thinks it's 48 pixels wide by 96 pixels tall, which is what we saw in the external memory Tetris game. It was trying to put these large blocks on the screen even though the display wasn't that.
Finally, we are going to talk about recommendations for future students that take senior design. The recommendation that I have is to start the project early. That way, when you run into problems, you have enough time to fix them.
The recommendation that I have for future seniors is that when you're working on hardware, you need to research everything and put as much forethought into it before you make any concrete decisions. Once you make a PCB, you won't be able to change things without taking a lot of extra time and spending more money.
The recommendation I have for seniors is to try and find a way to develop your software without hardware if possible. That was one of the things that actually saved our project around midterm and final checkoffs.